Hello and welcome back to this third and last video in the three-part series where I go through the presentation from my PhD defense. So in this video we'll look at how one can decide robust orbitally stabilizing feedback for trivial orbits and periodic orbits utilizing the sliding mode control methodology. So let's start with an example. So suppose you have given the task of generating oscillations of the Cart pendulum system. So this is a well-known system in which you have an unactuated pendulum attached to some cart, which you can actuate and force along the horizontal direction. So we want to generate oscillations of the upright pendulum while also having the cart making some desired periodic motion simultaneously. So we assume that we know some nominal model of the system, quite simple model, so corresponding to like Udist masses, the pendulum is a point mass with a massless rod and so on. We assume that we have used this model to already have designed an orbitally stabilizing feedback, which generates such oscillations of the pendulum about the upright for this nominal system. But it turns out that in reality, the model of the system is slightly different. So in fact, the cart is on a ramp of some inclination. The rod is a bit shorter. We have bits errors in our masses. We have friction acting on both the pendulum and the cart. We have some time varying disturbances, and so on and so forth. And so we are interested in seeing, okay, how will this controller we designed for the normal system actually work also for the perturbed system? So first we'll look at the normal control on the normal system. So this is the controller we designed on the normal system. It makes these small oscillations about the upright position as we expected. But how will it work on this on the actual model of the system? Well, not so well. But with the proposed robustifying feedback extension, which we'll show how to design shortly, we see that even with this, starting with perturbed initial conditions, it converges to something very close to what we wanted the system to execute, not perfectly as it's on a ramp, meaning that we have some unmatched perturbations we can't really do much about, but it does almost the best possible. So let's look at how one can design such switching functions for linear time invariant systems first. So this might, for instance, be a system obtained from a Jacobian linearization of a nonlinear system about some equilibrium point. So if we have a linear time invariant system, but with a matched unknown perturbation given here by delta. Now we assume that we know an upper bound of this perturbation and it's otherwise nicely behaved. We also assume that without this perturbation, the corresponding system is stabilizable, so that we know some matrix function m by n matrix function k, such that without perturbation, this matrix is Hurwitz, so stable. So we want to use now our knowledge of such a k to design an extension to our feedback such that the corresponding zero solution will also be stable in the presence of any such matched perturbation. This we can do if we can find a solution to the following lemma, specifically if we can find an m by n matrix S, which satisfies this determinate or invertibility condition, as well as annihilates a particular subspace of the unperturbed closed loop system. So if we can find such an S, then we can define sigma as shown here in terms of this S and the state Y, and then we can define the following feedback. So we take the normal feedback we knew for the unperturbed system, and we add to it this robustifying feedback extension. And this controller will render this zero solution also exponentially stable for any such matched perturbation if we take mu sufficiently large. So here we have this unit vector type controller, and we generally also define it to be zero if sigma is zero, but I just have written it here on this form for simplicity's sake. So this is interesting enough in its own sake, but how can we also take this idea and transform it to also design such extensions for nonlinear systems, and in particular also for more complicated types of orbits, such as, for instance, periodic orbits. So let's look at how we can extend it to periodic orbits of nonlinear systems. So we make a slightly similar assumption, but for the case of a nonlinear system now. So we assume that we know some mapping K, a C1 smooth mapping K, which provides us with a controller which would render for the unperturbed system the corresponding periodic orbit exponentially stable with respect to the closed loop system. So an unperturbed closed loop system. So we ask a similar question as we did on the last slide. how can we utilize our knowledge of such a feedback K to also design a possibly discontinuous control law for now a perturbed system? So we have some matched perturbation delta, which is upper bounded and otherwise nicely behaved. And so we are looking to find such a control law, so add to an extension to this K, such that the corresponding periodic orbit will also be exponentially stable for this perturbed system. So for this, in the thesis, a three-step procedure is proposed. The first is to find a set of transverse coordinates for the corresponding orbit of the normal system, and then to linearize their dynamics for the unperturbed system to the so-called transverse linearization. So since we linearize along a periodic solution, we get a linear time periodic set of equations. And we will then search for a so-called Floquet-Lyapunov transformation. So this is a particular transformation which allows us to convert the linear time periodic system into a linear time invariant system. And we saw how we could design an extension for such systems on the previous slide. So you can find a similar solution as in the previous lemma. Then we can again utilize this Floquet-Lyapunov transformation to go back to the original time periodic system, and then utilize a projection operator and other things to go back all the way to the non-linear system, providing us with a so-called invariant subspace-based switching function, which you can then utilize in a sliding mode controller to design a robustifying feedback extension. So this procedure is based on a patent application of two of my co-authors on the related paper, Leonid Freidovich and Sergei Gusev. So they proposed a method for a particular class of mechanical systems and a particular set of transverse coordinates. So in the thesis, it's shown how you can do it for a general class of nonlinear systems and for a general class of transverse coordinates, and not to mention a justification of this procedure. Now, the justification is based on the late Utkin's concept of equivalent control. So I'll briefly go through it here. So if we are given some switching function, so some sort of C to smooth function in the thesis sigma, then we are looking to find such a sigma so that the equivalent control when the system is restricted to the corresponding sliding manifold. So this is the zero level set of the function sigma, which we denote by capital sigma. So if we restrict the states to the sliding manifold and they are sufficiently close to the orbit, then the so-called equivalent control should have this form. So the equivalent control, loosely speaking, can be considered as the control which theoretically should be makes the system remain on the sliding manifold. So make the sliding manifold invariant. But often, in order to actually enforce this condition, you utilize discontinuous control laws. So in a sense, it might be loosely speaking again, considered like a average in a sense of the control which forces your states to lie on the sliding manifold. So the equivalent control, it should have this form. So it is equal to some mapping k hat minus this delta, which is our perturbation. So it rejects the perturbations, and then we are left with this k hat, and k hat should have some important properties. So it should vanish on the orbit, the same as the nominal control law we saw earlier, and it should be equal to this nominal control law in its first order approximation along the orbit. Now this means that if we can find such a sigma with such an equivalent control, then this will ensure that when we have forced the system states onto the sliding manifold sufficiently close to the orbit, then we will in fact have exponential orbital stability of all solutions upon the orbit in question, and hence it solves the problem we are aiming to solve. But how can we design such a sigma? Well, we utilize the procedure we saw earlier. So again, just go through the assumptions once more. So assume that we know some transverse coordinates for the orbit in question. So they vanish on the orbit and they have this rank condition. We then form the dynamics of these coordinates for the unperturbed system. So this is just the chain rule. And we insert the nominal control as shown here. Now we linearize these transverse dynamics along the about the orbit in question, from which we get a t-periodic linear system of this form. And for this, we do not necessarily need to compute it, but we denote by the state transition matrix, or the fundamental matrix of the system by this phi. And then we utilize this time scaling function we introduced in previous videos to make this, to parameterize it in terms of the variable s. Now parameter s rather. Now with these assumptions and properties in hand, we can search for such a switching function. So assume that we have now found such transverse coordinates to be computed for the transverse linearization we found state transition matrix. So we then will assume that can we find a C1 smooth and non-singular matrix function, a real matrix function of dimension n-1, so n-1 by n-1, and a Hurwitz matrix of the same dimension, which is also real, such that we can factorize the state transition matrix of the transverse linearization as follows. So if we can find such an L and an F, then we call this a Floquet-Lyapunov factorization of the system. And it provides us with this coordinate transformation, which we can transform the transverse linearization into a linear time invariant system if we can find such F and L. Supposing that we could, then much like we did for the linear time invariant system, if we can further find some sort of m by n matrix S hat, which satisfies this determinant or non-zero determinant or invertibility condition, and which annihilates a particular subspace of this matrix F, then using a projection operator and the transverse coordinates we assume we know, then we can define this switching function sigma with S perps shown here, and it has these properties we desire as we saw earlier. Now there are a few caveats here. So for one, we assume then, that we have this Floquet-Lyapunov factorization in which this L is ST periodic. But in general, there's no guarantee that an ST periodic real matrix function actually exists for this for a linear time periodic system. A 2ST real matrix will always exist, and you will also find an ST periodic complex set of matrices for which it exists. Now, even in the 2ST case, you might sometimes use these statements. There are, you can see, look at the thesis to see how this is done. And possibly it might also be possible for the complex case, but I have not fully investigated that. Okay, now suppose we actually found we're able to solve and find such a switching function. How can we actually design such a robustifying feedback extension from it? Well, we can add to it a unit vector approach similar to what we did in the linear time invariant case, for instance. You can also use other strategies depending on your perturbations. So like these multivariable super twisting types of schemes might works as well if you have Lipschitz continuous rather than just bounded perturbations. But for bounded, we utilize this unit vector extension. So we define V as shown here with this unit vector, and these are just some scaling terms. Now, if we take this zeta sufficiently large, then much like we did for linear time invariant system, we can add to the nominal controller this extension V, and it will render the sliding manifold of the switching function finite time stable if we assume that we have some input to state or forward invariance of a tubular neighborhood of the orbit. The reason for this is that in the nonlinear case, for nonlinear systems, we can have finite escape time of the states in the reaching phase towards when the states are in the reaching phase to the sliding manifold. There might be, for certain systems, you can utilize certain structural conditions to remove this assumption, and perhaps it's also possible for certain additional conditions on this zeta to also ensure local input to state stability, for which it holds also for a class of nonlinear systems. But this will be likely highly system dependent, I think. Okay, this was the procedure in a super fast nutshell. Thank you very much for watching.